I will start then. Hello, everyone. It's with great pleasure to have the opportunity to present our work at LMPL today. I'm Stephen. I'm a master's student from the University of Toronto, and today we will be presenting our work on repository-level program verification using language models, where we try to extend some recent AI techniques into making verified software at larger scales. So in today's talk, I will first do a quick recap on what is formal verification. Then I will show how we extend and evaluate language model methods on large-scale software repositories using a new benchmark and a new context management framework. So a quick recap on why do we need formal verification. In usual software development, we try to make reliable software through test cases. However, those only capture the presence of bugs, but not the lack of any bugs. Where in formal verification, we parse the program behavior into a mathematical model where we then do reasoning and proves properties such as safety and liveness that are hard for test cases to catch. And some real-world examples that require high assurance is like flight control systems or OS kernels. To achieve verification, there is the cost of completing not only the implementation, but you also need to write the formal specification and completing the proof process that connects everything together. In modern verification tools like Daphne and Verus, they allow programmers to write these spec and the proof code in line with the executable code. So on the right-hand side, it's an example of a verified Verus program. Verus is a verification extension based on the Rust programming language. So we can see in yellow and in orange, we are writing spec and proof in concatenation with the implementation itself. These kind of verification-aware languages not only give a more readable and intact format for developers to work with, they actually also already automate a lot of the underlying logical reasoning. So given a simple problem with simple spec and executable, the Verus tool actually can automatically generate the verification condition, passing it into the SMT solver and letting the solver give a satisfiable proof. However, in many cases, programs aren't simple. And when we just pass the simple translation between executable and the specification into the solver, they cannot give a deterministic solution. And that is when we need to provide manual proofs aiding the process. Where with the additional proof, we will have additional condition that helps with satisfiability. So even though the tools already streamline the process a lot, it's not fully automated. Specifically from what we observed in real-world repositories, it's very common to see only 20% of the code lines being implementations, where the rest 80% are purely for verification purposes. And specifically with the huge amount of proof completion required, this is actually non-trivial. It's fairly difficult and requires expertise to come up with good looping variants verifying properties about the programs, which can take even experienced users a long time to complete. And with that, this work we specifically study the proof completion problem on a repository level setting, where we believe these larger repositories reflect a more practical situation of how software development is completed, where the not only the volume is huge, but things are modularized into different files and components. And we assume and operate on a partially verified repository where many of the other functions are verified, but we are left with a few of the unverified functions missing the proofs. We are given their spec and executable, but we still need to verify the software and the function itself. So the repository setting does add additional complexity, first and foremost because of its huge context. There's thousands of functions and type definitions we need to work with and reason about. There's also the problem of cross-module definitions, where a helper function needed for this proof may be residing in a different file that is not currently accessible or not apparent. And within the repository level, because of so many lines of specification and proofs, it's really hard for anyone to follow on the strict syntax, streamlining the proof process. And in our work, we try to examine how we can utilize large language model capabilities to complete this proof process. And specifically, if we directly feed all of the problem and the entire repository into language model, it's fairly costly, and I don't think even today's model have the capability to ingest everything at a time. And because language models are actually fairly poorly trained on these verification domains, they also don't have a good knowledge about how to do these tasks. So it's very important to, in order to achieve higher accuracy, we need to provide a precise context and guidance to the language model. We address this by using the Verus tool that we will be talking about, where it is a retrieval augmented method for context management. So specifically, we try to retrieve two types of contexts using the Verus tool we are presenting to aid the language model. The first thing is what dependencies and premise does the current proof completion task require, where we try to identify previously defined help functions that is already existing in the repository that can be used in the proof process directly. Secondly is about pattern understanding. We need to teach the language model how to approach this particular task in terms of the proof pattern and practices. So we want to find how similar functions are proved and using that as a scaffolding for the proof of the current question. And next, I'm going to give an example on how we extract these two contexts using an example from a real-world repository containing unproved function. And in turn, we show how this retrieved context aided the proving of this particular unverified function. Here it's very small, but we look at a real-world example on a implementation of a locking mechanism, where we have a function called lock release that is unverified. It has the implementation code and the specification that can't be verified by the SMT tool automatically. From here, we try to find useful context about this function by looking at other similar functions within the repository. Specifically, we define similarity by two means. First of all, if there's other code that is similar to the task code in terms of the syntax or semantics. And secondly, if the other code has common static properties, like what kind of type definitions are used. In this case, there's in the parameter list, there's a lot of tracked variables. So maybe that's a hint of what we want to look for. And also, if these files reside in similar file organizations. And luckily, in this case, we are able to find another example function that is already verified. So this is the lock acquire. We can notice that within the acquire function's proof, it uses some dependencies, such as this one called tracked insert, that is a helper function it uses. And secondly, we also notice it uses some practice of having actually a ghost helper variable declared before doing the proof assertion command. So we actually extract these two contexts as helping informations for the language model and pass that synthesized context back to the language model in order to prove our original question about how do we prove the release function. So in this case, we are able to successfully use the retrieval method to gain a much better context about what we are doing and how to do it. So in order to achieve such context retrieval, we need to prepare the corresponding search indices in order for efficient retrieval at runtime. We do it on a per function basis. We do the indexing on a per function basis. For the first index, we turn the function code directly into high-dimensional embeddings and store that for similarity search in the future. Secondly, we extract the metadata about each functions. Things like we've mentioned, what kind of type declarations are used in the function, any class inheritance associated with the particular functions. Many of those come from similar terminologies in context organization from program generation in general. So we then summarize this metadata and index this into a separate index as well for a quick lookup at runtime. This is a sample of what metadata may look like. And these items set up our main pipeline for the reg Verus. So when given a repository, we want to first create the corresponding indices by parsing the context, and then when given a particular proof completion task, we are able to retrieve the useful context through either code or the metadata, and help language models reasoning with the pattern scaffolding or the helper function extraction process. Lastly, we pass the synthesized retrieval results to language model for final generation, and this is a visual flow of the process. So in the indexing and the retrieval we've talked about. After that, it's the proof generation process, where we either choose to do a direct generation based on the context and problem we give to the language model, or in additionally, we can do a refinement process where we take the feedback from an error message from the verifier or compiler and let the language model try to auto-correct itself again on how to repair the proofs. So with that, we want to put this into evaluation. We introduce a new benchmark called repository verification benchmark, RVBench. It is the first kind of benchmark in this kind of verification-aware language dealing with repository contexts. And it is sourced from 4 complex and real-world Verus projects, offering a diverse verification testbed, ranging from things like verified Kubernetes controllers to verified distributed key value stores. Here's an overview of the specifications. But in general, we are able to provide 750 more proof tasks covering more than 12,000 of proof lines. And among the verification tasks, to the maximum, the verification problems aren't trivial. To the maximum, we can have some functions requiring more than 80 lines of proofs in order to prove a single function. Lastly, the logic breadth required to do this proof completion on this benchmark. These task problems in RVBench capture some kind of logic ranging from linear logic to separation logic, which deals with memory safety guarantees or concurrency guarantees and more, which is more complex than what previous benchmarks provide. So lastly, to evaluate whether a completed proof, for a function is actually correct, we need to evaluate the success, and it's measured by being verified and intact at the same time. Verified meaning the completed function compiles by the Verus compiler and passes its verification process. And intact meaning the original spec and executable aren't altered. Here we'll just provide a very quick highlight summarizing the key evaluation results. The baseline we compare to is AutoVerus. It's another proof completion tool for Verus, but does not have the smart context retrieval capability. And for our side, we provide 2 invariants concatenating our context retrieval method with either direct generation or refinement. And we can see in all cases, with the context smart context retrieval, it's able to perform a lot better. And we believe that specific and task-guided context are promising in reaching better software verification. I will leave anything else for questions, but that's the main thing I want to cover on the core of our project. Thank you for listening, and I will welcome any questions.
So you mentioned that part of this was ensuring that the specifications were unchanged and the implementations were unchanged.
Yes.
Yes, but I think in practice, it's sometimes necessary to strengthen a specification in order for a proof to go through, or perhaps change even the implementation, not the ultimate result, but change the implementation to perhaps use less strange language features to simplify the proof.
I see, yes, definitely. In real practice, it's fairly more practical to have the iteration loop between implementation spec and the proof, right? In our setting, it is a more of a simplified situation where we assume we have a good idea about what the program does. So there is a specification given, and there is somebody already gave implementation. So we are just doing the proof completion, verifying whether they match.
I see. I was just curious though, if you were thinking to extend to a context where maybe the specifications themselves don't fully specify the behavior, how would it be possible to extend this approach to that, you think? Or?
Yeah, yes, specification, especially auto-formalizing specification from other sources is a difficult problem, and it's not a particular target of this task. I know there are many other exciting work. There's recent Verena or some other verify benchmark that deals with this end-to-end thing.
Cool, thank you.
Hopefully it answers some of your question.
And that one task contains more than one function?
Currently, we only complete one function at a time. Right. So our statistic doesn't show a union over multiple completed functions.
Right, thanks.
So you showed in the benchmark set how many lines of proof code were needed to verify the property, I believe. But that's in the original benchmark, right? Or wait, you didn't show this on the presentation. So I was actually wondering how readable the resulting proof is compared to human written proofs.
I do have another slide showing a blue score comparison, which compares the text similarity between generated proof and the human written proof. With the RAG-based methods, it does show an increase in the blue score, so the generated answer actually more closer to what the human write, because of this in-context example, but not particularly on manual inspection between exactly how readable they are.